to deliver the endowment lecture this year. All of you know him well. He is an outstanding theoretical physicist and excellent teacher. I will be very brief in introducing him. Professor Sriram Ramaswamy received his BS in physics from University of Maryland College for US. So he got his degree in 1977, and then he moved to University of Chicago, where he received his PhD in physics in the year 1983. I understand that Professor Sriram is associated with this institute for more than 35 years. Currently, he is an Honorary Professor and J.C. Bose National Fellow at the Department of Physics at this institute. During 2012 to 2016, he served as the Director of the Center for Interdisciplinary Sciences, TAFR Hyderabad. His research mainly focused on non-equilibrium, soft matter, and physics of biological systems. His work on active matter helped understanding the mechanics and statistical properties of cells, tissues, and organisms. He received several awards and recognitions for his outstanding work, which include the Shanti Swarup Bhatnagar Prize, the Infosys Prize in Physical Sciences. He is Fellow of the Indian National Science Academy, Indian Academy of Sciences, and National Academy of Sciences, India. He is, at the age of 59, he was elected as a Fellow of the Royal Society. And today, he will be talking to us on non-mutual feelings, odd mechanics, and singular structures in non-equilibrium matter. It is a great pleasure. I invite Professor Sriram Ramaswamy to deliver his speech.
Thanks very much for that very kind introduction, and I'm very, very grateful to be asked, honored to be asked to give this in our endowment. First, quickly, a couple of words about my connection to Professor Rao. He was director when I joined this institute, and right from the beginning, what I liked was his interactions with young whippersnappers like me who just arrived and talk too much and so forth. Extraordinarily, not just indulgent, but receptive and interactive, and really enjoyed talking. Of course, he supported what we were doing, and he also had a keen appreciation of areas like, theoretical physics, which wasn't his game by any means. He went out of his way to support the whole condensed matter theory enterprise at IISc. So I'm delighted. I'm sorry he's not here, but I'm really delighted to be giving a lecture that he has done. So thank you very much. As Mukesh said, I've been here for 38 years. It's not the first time I've given a talk in faculty hall, but it always feels very special. Let me start. I should apologize. It's sort of a ridiculous title, invented under pressure, because when you give a lot of talks, especially a lot of overview talks, you kind of run into an orthogonality catastrophe after a while. Because for those of you who like a maths, you want each talk to have minimal overlap with the previous one, so you go on doing this ground sprint in the space of talks, and sometimes you run out at least of titles, to say nothing of content. I'll try to actually cover topics that are related to this gloomy title document. I'm also at ICPS, and I thank SCR, BOA, and IF for support. Okay, let's start. What is it? This is a 16 by 9 page, the projection is kind of square. I guess it would be like that toward the top. Yeah, but everybody is thinner than they actually are. So that's the group. I'm showing you their pictures because I won't be talking about everybody's work by any means. I'll show you I'll mention specifically whose work I'll talk about. There must be some, no, it must be this aspect. No, try something else in aspect. Better, yeah, great. Thank you. And these are many alumni over the years. So, too many to this. I think I missed one. I missed Thibaut, who just all right. So, in keeping with the weird title, I've also given you a weird outline, which contains the weird topics of the weird title. So, in sequence, after an introduction, I'll talk about the three topics I mentioned. I think not in the order in which they appear in the title. Okay, all right. Okay, so I somewhat ambitiously gave a very general statement about that I'm going to talk about non-equilibrium matter broadly. Roughly speaking, if you've got a collection of particles interacting with each other, you can imagine that they're non-equilibrium either because you are driving them, let us say, as in this example of particles sedimenting under gravity through a fluid or through some medium, it's not a fluid, or they have some internal motor. So they have a storehouse of fuel and they're doing something. So broadly you can divide out of equilibrium systems. Every particle is being directly driven, as is the case under gravity here, or under an external drive here, or internally. You can also have something much more boring. You've got a wire and you attach a battery to it. So then the driving is only imposed in the potential difference at the ends, and internally, if you like, the dynamics is driven only because things are being pushed from the boundaries. I will say a little bit about this class of problems, but more about this. Unfortunately, I will not give you a theory of the military liquid crystal in this talk, although it's sort of on my agenda of things to do. Okay. Just to illustrate the kinds of things that an externally driven system is capable of, let me just show you why I said that sedimentation is an interesting problem. If you've got particles moving through a fluid, their dynamics is strongly coupled and gives rise to interesting instabilities, which I may say a word or two about in the talk, although it won't be the bulk of my talk. Alright. I'll mostly talk about systems that are active, and when I say active, I mean that each effective constituent of the system is powered. It could be powered because it has a battery pack or some chemical fuel or something, or it could be powered through somewhat more shady means, which I'll show you during my talk. Obviously, the reason for inventing this category of matter is to be shamelessly able to annex the living state as one more kind of condensed matter. And that's really why the term and the field was invented. The idea is that each particle is in a sustained way turning free energy into work, which means it also has a sustained supply of free energy. As it eats, it keeps getting fed more, right? And so these particles are different in some way. They're not seriously different from any other non-equilibrium system, but the idea basically is imagine you've got a collection of particles, say lying in two dimensions, and you pump energy into them in a third dimension. Then what's happening is the way in which you are pumping energy in isn't breaking any of the spatial symmetry. So if you've got stuff lying on a surface and you feed it energy in the third direction, then the in-plane dynamics has the potential to display all the nice symmetry breaking phenomena spontaneously that we like to study in ordinary physics. So this is why it's kind of convenient to define active systems where you don't break spatial symmetries, but you break time reversal in this way by supplying power as a distinct kind of matter. Okay? And a big part of what one is interested in is just the ways in which active stuff is different from non-active or passive stuff. But obviously you want to do more, you actually want to understand biological function, you want to understand maybe you make gadgets that do something interesting, etc. I haven't had any great success in the latter activity, but this is a field that's overpopulated with review articles. This is one of the many ways in which it resembles biology. Achha, how many in the room are not from physics? Oh, good. Okay, there's at least. So I dissed the biologist. All right, and the motivation, in a sense, is to understand living material as a special kind of condensed matter, and hopefully to do predictive theory and model experiments, maybe cook up toy systems that imitate some of the features. But from my point of view, even if it doesn't have a great impact on biology, if it has an impact on giving you new kinds of physics, that's already good. The other point I want to make is a big part of the success of active matter has been to take a very lowbrow view and say that we know that physics enters biology in two overlapping but distinct ways, namely through mechanics and through information, right? And a lot of what we've done in active matter is to not worry about information on any time scale. Biological information processing takes place at every time scale from instantaneously protein synthesis to evolution. But imagine not worrying about any of those. The focus has been on that mechanical aspect. But a natural way to go from sort of purely mechanical active matter to something slightly more serious is to at least start to look at sensing, signaling, response to gradients and so forth. And in some very limited way, I'll say a little bit about that. Okay, this slide or variants of it has been inflicted on my friends many, many times over the past more than 2 decades, but I have to do it. As in ordinary condensed matter, so in active matter, you can have particles which are structurally of various kinds, and you can have ordering phenomena which are characterized by a scalar order parameter, more complicated order parameters like tensor and so forth. Okay? So both at the particulate level, you can have a particle that's round, a particle that's pointy, a particle that's stick-like, and you can have spatial arrangements that just are described by a density, or are described by some vectorial orientation, or are described by an axis without a head, and many others. You can also break translation symmetry and so forth. The other important thing, and much more important here in these active systems than it is in equilibrium systems, is that the system can lie in a different dynamical ensemble. I mean, let me give you an example. Supposing lots of you know how to do Monte Carlo to get phase diagrams. And you know that if you have a collection of particles at thermal equilibrium, whether you do a Monte Carlo in which the dynamics conserves momentum or doesn't, as long as you have a given energy function, will give you the same phase diagram if you're at thermal equilibrium, right? You can do just plain Monte Carlo, you can do MD, you can do various variants there. In out of equilibrium systems, even what kinds of phases are allowed, it turns out, will depend on whether you're in a momentum conserving or momentum non-conserving situation. You can't pass freely between ensembles in that sense. Again, if you have a collection of particles which is doing some kind of dynamics out of equilibrium at fixed number, there is no simple way of mapping that phase diagram to a phase diagram at fixed chemical potential, for those of you who grown up doing these kinds of things. Okay, so it's good to keep all this stuff in mind. And the sort of unease which this gives one is what makes the subject interesting. Okay, I mean, just to give you an example of, so we call these dry and wet active matter, the different fluid ensembles. And here's an example of wet active matter, Vishnu Guttal's Karimine. Where is it? Huh? Yeah. I don't know if you can see it very well, but just phenomena like this, frankly, we haven't really understood yet. Okay, and they're clearly fairly local, and there's clearly physics rather than just, pure stimulus response behavior going on here. Anyway, I mean, I can show you other pictures, but I won't. Now, this is a lecture endowed by a chemist of extraordinary eminence. I also noticed that the first speaker in this series was George Whitesides. So as it happens, some of the work he did about 25 to 23 years ago is central to the creation of artificial active systems. Suppose, what does physical, or what does metabolism, what does any of the life processes that go on in us consist of? Taking stuff at low entropy, doing something with spitting stuff out at high entropy. Okay? And why is the stuff at low entropy surviving? It's because it's metastable, right? So if you have a particle on which is a little dot of catalyst, and you put it into a medium containing what chemists confusingly call a substrate for that catalyst, this little patch will break down that compound, right? And as a result, you will get a gradient along the surface of the particle of the stuff that's broken down. There'll be less of it near the catalyst, more of it away. If you can keep the reactant, the substrate, maintained at some level, then you will permanently create a gradient along the surface of the particle, so fluid flow will take place over the surface of the particle. So you can make things that swim. As long as you keep the fuel going, you can make stuff that swims. So it goes back to Whitesides, and then Ayushman Sen and group did it with much smaller particles. These were great big centimeter size particles. And the theory of it was produced by Golestani in Liverpool and Ashdari some years after that. So this is chemical active matter. Basically, you've got a particle, you know, and it's a perfectly reasonable example of a motor. What is a molecular motor? A molecular motor is an enzyme whose enzymatic activity happens to be coupled to translation, right? It takes fuel, it turns it into something, and it walks. So this is actually a very good imitation of, but my interest, so I actually in this talk won't talk about those kinds of systems at all. I'll talk about sort of mechanical active systems. It's convenient if you've got a surface and you pump energy through that surface through many different kinds of means, okay? It could be that you got a little colloidal particle sitting on the surface with bulk fluid around it, you apply an electric field, and the overturning dynamics of this object, if there's a mismatch in the time scale of how the ions move and how the particle moves, will start this thing rolling. The field isn't even oscillating, you just have to have ions there, okay? And these guys will start moving, and you can make a flock of these. You can take particles with a little magnetic moment on their side, like Ambarish does, and apply an oscillating magnetic field, and if they're twisty things, they'll start walking. You can take a droplet, and if you can somehow make the droplet maintain a wettability gradient between the two sides, it can start walking. So there are lots and lots of colloid scale physical ways of making things that self-propel. Okay, but our favorite is something sort of at the level of a child's toy, right? So you have a surface, you shake that surface up and down rapidly, and you put something on it. Okay, now there's a lesson here. When you shake the surface up and down, you think, look, it's just noise, right? If I put a particle on a noisy surface, it'll just dance around. It should do Brownian motion. Actually, it's not true. Not all random agitation is, I'm sort of, my introduction is taking too long. Actually, if you get the story of the introduction, the rest is just examples, which you can do for homework. Okay, so, but I'll try to get to the meat of the talk. And so you shake this stuff up and down, and then depending on the asymmetry of the particle on the surface, it will either jitter around as though it's doing thermal Brownian motion, or if it's a long particle but the two ends are the same, two ends are structurally similar, then it will just move back and forth along its length, or if the two ends are sufficiently different mechanically, then it will start walking. So I won't show you a movie of the sphere because the sphere is like the dog in the night. It does nothing. If the particle has two ends which are very similar, then what it does is kind of funny. It moves back and forth in a random way. It's not a sustained oscillation either. So this is a particle which has more kinetic energy along its length than transverse to its length. That breaks equipartition, right? So you can be out of equilibrium in a very subtle way. And if the particle has a well-defined head and tail, then like this particle from Nitin's experiments, it'll walk. So this is a top view. I'm vibrating the thing like this, particle is walking. And on long time scales, it changes direction, okay? So it becomes motile. And you can imagine that if you put a bunch of these together, you can actually get flocking and other phenomena. Okay, it's important to realize that our motile particles are walkers, not swimmers, whereas the other things I showed you, the things that roll in a fluid, there the main momentum balance is between that particle and the fluid around it. The substrate serves a little purpose. Here the momentum balance is really like when we walk, okay? If we have an oxygen tank, we can walk in vacuum. We're not swimming and crawling, right? Okay, so these are crawlers or walkers. And these systems are therefore nice because the medium around them, the bulk medium around them, isn't the thing that's responsible for their movement, you can add particles to that medium. You can strew a lot of little spheres in the substrate and modulate the interaction between these particles. In these guys, changing the fluid just changes the clock speed. You can't, you don't increase or decrease the interaction between the particles. Okay, so that's the sort of long introduction.
Change with frequency and amplitude?
Yeah, so I mean, it depends. Which system are you talking about, the electric field system or our one? Yeah, so I mean, okay. So what we do is, when you look, you take macroscopic grains strewn on a surface, there are many kinds of phenomena that take place. I mean, Raman studied some of them and so forth. So, if you have a substrate without a surface without a lid, then heaping can happen, and there are important frequencies there. Okay, clearly one natural frequency is the free fall time, 1 upon the free fall time over a size of a particle, because you have gravity. There are other things. But our aim is to stay away from those and kind of make this a very kind of agnostic source of energy input, which doesn't create specific behaviors by changing the frequency. In our experiments, I never did the experiments, joint students with Ajay, with Narayan Menon and so forth. The idea is that in those experiments, we want, we always work with a lid. We want to stay away from the interesting classes of phenomena that take place when you have vibrated stuff on a surface. There's a big literature on that. Harry Swinney, for example, has done many beautiful things on it. Okay, so let me come to section 1 after the introduction, which is on non-mutual feelings or non-reciprocal interactions. The term non-reciprocal has kind of taken the non-equilibrium statemic world by storm. It is in part a marketing term. And the reason is that people have known about this for a long time. Okay, any kind of sensing and signaling is non-reciprocal. You have a ligand, you have a receptor, potential. But what happens after that is a long signaling cascade. What the ligand and the receptor don't have similar lives at all. Okay, and in real life, of course, we're familiar with this kind of things. Interactions between human beings are very, very non-potential. But in fact, even when you have collections of organisms that form swarms and flocks and herds, in the case of one type of locust, the interaction is this non-reciprocal. The one at the back wants to eat the one in the front wants to escape. The result is that their orientation and velocity vectors align with each other, and they have a phase transition to an ordered state to save their lives, okay, or to eat. But in general, asymmetric exchange, all of these things are examples of non-reciprocal interactions. It's important to note that non-reciprocal interactions are ruled out at thermal equilibrium. Suppose you've got a bunch of particles, let us say you've got particles in a fluid. Then even though given you've got two particles and an ambient medium, the interaction between these two doesn't have to conserve the momentum, conserve momentum and energy between them. There's an ambient fluid which can take up the slack. Despite that, the effective interactions, that is the thing that governs the phase diagram of a collection of interacting particles at thermal equilibrium, even if there is a medium around them, is effectively an energy function. And a way to see that is to think about writing down a master equation. If you write down a master equation for a system where these are just microstates, then you know that the particular kind of stationary state you get at thermal equilibrium obeys a thing called detailed balance, which says that on any link between two microstates, the net current should be 0. What that means is the steady state should be such that occupancy of a site times the transition probability to another should be the occupancy of the other state times the transition probability back. This can happen globally only if the transition probabilities satisfy this condition. This condition is a kind of curl-free condition. It allows you to construct the steady state very easily by starting with one site and labeling it P, and then correspondingly labeling all the other sites by ratios of transition probabilities. And it shows that finally you can do this only if for each pair of microstates, this transition probability ratio, or the log of it, is a function of the difference of a quantity which is assigned to each site, each state. Okay? That means that even if you didn't know there was an energy function, the fact that you have detailed balance tells you there is an effective energy function, and that means that dynamics of the system is effectively a gradient of this energy, and therefore the interactions amongst the particles will have to be such as to obey an effective Newton's third law. Okay? Clearly, if you break it, that won't, and that's really important because that's the thing that allows directional transmission of information and so forth. Okay? All right. So that's non-reciprocality. So what I'm going to show you now is a sort of childishly simple example of non-reciprocal sensing and signaling and movement. The experimental system is the one I mentioned briefly at the beginning. It's this machine that we've now been using for, I don't know, 15, nearly 20 years. It's an industrial shaker. And you have particles. All of this stuff is really big, okay? These are not colloids, not molecules. These are sort of machine parts. That's like half a centimeter in size. Thickness is about 1 millimeter. This is the sample cell looked at edgeways. It's not very big. One of the tragedies of this kind of physics is you are nowhere near whatever passes for a thermodynamic limit in these systems. System size to particle size is like, if you're lucky, 20 or something. But you can make much bigger ones. If you make very, very big ones, the difficulty is that the modes of the support structure start to become important. So it's better to do colloidal versions instead. Anyway, so you do this, you shake it very, very fast, 200 hertz, tiny amplitude, which amounts to some 7 Gs. And you will put different kinds of particles in here and see what they do. Okay, so for example, in this thing, what we do is we actually were looking at, this is a particle moving through where is this? Moving through a medium. So there's a monolayer of these spherical particles, which here are so densely packed that they are a crystal. Notice they are not jammed. They're merely frozen in place, but they agitate around. And this particle, moves through that bead bed like a two-dimensional armor-piercing shell of some kind. And the physics of that is one of the things we'll talk about. Okay, this is, part of this was Rahul's PhD work. Part of it is Roshan's PhD work. Roshan is finishing off now. And it descends from earlier work by Harsh, theory and simulation, and all jointly with Ajay Sood. Okay, so driving through a crystal. How would you do a theory of this? Okay, very crude system, right? I've got a particle. Each particle, imagine I have one, okay, I'm going to call these polar rods and I'm going to call these beads because they actually are beads. They were bought from some Rakhi manufacturer in Surat or something. This guy has a position R and a unit vector of orientation N. And a crude model of its dynamics is that it follows its nose. It moves in the N direction with a speed V0. Okay. This layer of beads I will describe by two-dimensional Lamé elasticity. Everybody from the engineering department should know what it is. Some of the physicists may also know. Okay. So ordinary two-dimensional elasticity. So let F be a standard Landau-Lifshitz free energy functional for the displacement field. U is the displacement field, not the velocity field, the displacement field of the particles. Okay, and the whole thing is sitting on a substrate, so it's a momentum sink. So the drag on any given bead sliding or rolling across or moving across the substrate is proportional to its velocity, I'll assume, because I'm assuming it's sort of been agitated enough that things like static friction and all I don't worry about. Okay, so drag is balanced by elastic forces, elastic restoring forces of this bead bed, and the force that this single motile particle exerts on the system. So this is a very easy equation, right? I've thrown away inertia completely, instantaneous force balance between drag forces, driving forces, and elastic restoring forces. Third part of the story is, this orientation is the orientation of an object placed in an elastic medium. Now if you take a rubber sheet and you put a little stick on it and you stretch it, it'll sit in certain directions in it, right? So if you extend or squeeze, things like to sit along extensional axes. That's one part, okay? So that will say that the orientation changes to the extent that it wants to point along the principal axis, let us say the extensional axis of the strain. There's another part of it which I'll show you in this picture. So this is aligning along the extensional axis. This part doesn't care about the head and tail of the particle, just the axis. A part that cares about head and tail is if I bend the crystal planes here, crystal lines. If I bend or splay them. Then I define a vector and my arrow may like to point in the opening direction or the closing direction of this, depending on some mechanical properties. Okay? So these are the equations of motion. So you take these three equations of motion and ask what happens first to one particle, and then to two particles, and then to many particles.
it turns out even one particle has something very interesting, which has important consequences for two particles.
Sorry, what is I?
Where is I? Oh, unit tensor, identity. Sorry. Yeah. By the way, I wasn't sure how many people from what department would come, and so I wasn't sure how to design the talk. So what I'm doing is I'm throwing equations on the screen, and I'm talking without equations, which somehow maybe is okay. All right, so the fun thing is that even one particle moving, so now let's look at this equation. Okay, supposing nothing was moving, but there was a little force here. Then this equation would simply be an equation whose solution would be the elastic Green's function of this two-dimensional thing, right? I've got elastic force, and I've got a little point force where the particle is sitting. So the displacement field should just be the two-dimensional elastic Green's function. But it's actually very different. Why? Because this little guy is not only exerting a force, it's also moving. As a result, let's do a very simple thing. Let's forget about the fact that actually, even though Lamé elasticity is isotropic, what a little vectorial object put into this medium sees is not an isotropic medium, but a medium with whatever point group symmetries this structure has. Let's say it's moving in some direction. And let's sit on the particle. If I sit on the particle, I'll see all time dependencies will just be a directional derivative with respect to the direction in which I'm moving. So the displacement field will satisfy an equation in which that time derivative has become derivative in the direction which the particle is moving, and elastic forces and point force now situated at a fixed place. So I can solve this. Turns out I can solve this by doing something called looking up Gradstein and Rijik. And this room will be divided into a very large number of people who don't know what that is, and a very small number of people who do. So you solve it. And what you find is it gives you these Bessel functions, modified Bessel functions of various kinds, zero. Okay. And what's interesting about them is what they tell you is that these guys have got exponentials in their asymptotic behavior, and there's these outside. The result, it turns out, is that basically we take this particle and look at what strain it produces in front of it and what strain it produces behind it. It turns out in front of it, the strain is very rapidly damped. There are two length scales based on the ratio of the drag force to the elastic constant of the drag force. Lengths that get bigger and bigger the slower the particle is moving. And so the moving particle has in front of it a very rapidly decaying disturbance, and behind it a very slowly decaying disturbance. Okay, for fluid dynamicists, it's a lot like the Oseen modification to the Stokes solution. Okay.
So is V not smaller than the speed of sound like that?
Okay, so there's an interesting question. All this stuff is lying on a surface. There's no serious sense in which you can talk about the speed of sound because it's,
The elasticity of that.
No, I know, but an elastic medium on a damping substrate, which damps the momentum, momentum even at zero wave number, is asymptotic. Everything is utterly overdamped. There could be, if the damping is very low, you could have a window of length scales in which, and I don't think this system is that. This question comes up again in the second half of the talk if I let myself get there. But yeah, so.
Given the general news around, maybe if it is hypersonic, it can give rise to certain Mach.
So, what you get here is not a Mach cone, it's a different wake. I'll come to, there's some shock physics that comes up later also. I told you singular structures, no? It's actually there. Okay. You can calculate these displacement fields, and they have the x displacement, the displacement along the thing has this very asymmetrical form. The transverse displacement has this form. To a parent's loving eye, these measured displacement, measured by the way, not in a true experiment, but in a computer experiment. That is saying, the computer experiment didn't solve the PDEs. The computer experiment reproduced all the mechanics. The heroic work by Harsh to create this simulation box in which he reproduces every bit of the mechanics. And so he does a measurement, and at least, as I said, to a fond parent's loving eye, this curve looks like this one and this curve looks like this one. And if you take the parallel displacement and multiply it by root x, then you find something that's non-decaying behind the particle. The prediction was x to the minus half behind the particle, exponential in front of the particle. I will not claim that's an exponential, but it is what it is. These are not easy measurements to make because that will take me a long time to get into. But it's really fun because you can now ask, if I put two particles into the system, what happens? Okay? If I put two particles into the system, what I'll do is I'll do an approximate calculation in which I'll calculate the strain field due to one particle and look at its effect on the other through this equation. I can do something better than that, but there is a sort of, it's the first step of an iterative solution. Okay? So I've got two, so what I have is I take one particle and put it in, let us say, pointing upwards, and I take another particle, put it in this way. Remember what I said, the particle's disturbance is very, very screened in front of it and very slowly decaying behind it. So what this means is that the particle, if a particle can sneak up on a particle ahead of it and do a kind of stealth attack, the particle in front will have no clue that this guy is coming. The guy that's moving has left a nice, long, slowly decaying elastic trail. So this one can sniff that out. So this is this is sensing and signaling. And it's non-reciprocal because the effect of this guy on this guy and the effect of this guy on this guy are totally different. It's no surprise any kind of mediated interaction has this property. The point is, what makes it different is whenever you have a situation in which the degrees of freedom have part of their motion entirely autonomous, like these guys are motile, okay? So how it moves is primarily dictated by how it points. Imagine, this is roughly true in this case, that its speed is more or less unchangeable. All that changes is its direction. So then the interaction is not like a force which produces an acceleration. It's taxis for the biologists, okay? It's a kind of elastic, it's like chemotaxis but using elasticity, not chemistry, not concentration, okay? So this guy senses that guy through a field that decays slowly with distance, and that guy actually can't sniff this guy, okay? And so you get this. So in fact, theory says that the particle at the back will actually follow the trail left by the particle in front and catch it. You can simulate it, and it's satisfying to see that you can see this in the experiment. So it doesn't kill it or eat it or anything like that, but it catches it, reaches it. We haven't made particles that know how to do anything more than that. Anyway, so that's so what is the purpose of that exercise? The purpose really is to show you that phenomena like non-reciprocal interaction and taxis and all that don't need that much. Once you have a degree of freedom that's driven in a sustained way, basically all your naive intuition is off, and you can start to do things that are surprisingly clever, considering what have I done? This is just a surface that's vibrating. These particles walk because their structure makes them walk. And that's all. And there's a medium. Okay, so you can start to imitate. I mean, again, it's a big exaggeration to claim functionality or something here. We haven't done anything with this, but it's kind of nice.
What's the blue curve or the red?
Two particles, red particle and blue particle. And the blue particle is moving along oblivious of the red particle coming up to catch it. And the red particle knows very well where the blue particle is because of the x to the minus half wake.
So
yeah.
Can I naively conclude that simulation is closer to the experimental result than simulation?
Say it again, simulation is closer to the?
Three plots here.
Is
it correct to assume or conclude that simulation is closer to the experiment than?
To be fair, these are sort of anecdotal. The real problem is that there's some important things missing in the theory. One is the theory doesn't take into account the intrinsic anisotropy of the material. Secondly, these are noise. The calculation in the theoretical calculation is done without noise. Actually, when you start these particles out, they don't immediately start moving. Sometimes they're slightly stuck. There are some delays. There's lots of imperfections, and the simulations have most of the imperfections the experiment has. The theory, to put the imperfections into the theory would require putting in more structure. So in that sense, you are right. But yeah, the theory is a very simple-minded theory. As I said, all of you know that two-dimensional six-fold symmetry is enough to give you isotropic elasticity. But a two-dimensional solid with six-fold symmetry is not an isotropic object. It's an object with six-fold symmetry. Elasticity can't detect it, but a little vector object placed inside it certainly has preferences about direction. So all of those things make a difference, because the theory is isotropic elastic continuum. Right? Yeah?
So the reason that the second particle does not...
Yeah.
second particle kind of comes in a stealthy manner,
Yeah,
but it's not detected by the first
yeah.
particle. Is it because of this exponential?
That's what I said, yeah, exactly, yeah. The point is that your displacement field is exponentially screened in front of you and completely unscreened behind you, decaying only as distance to the minus half. It's exactly that.
So the two particles, otherwise the field profile, everything.
Everything is the same. The point is that interaction is not through a pair potential. If their interaction is through a pair potential, no way it could do this. This is a tactic interaction.
What if one just say hypothetical? What if this particle is coming perpendicular?
I mean, there are lots of cases. I can show you other movies. Yeah, so I just wanted to. It's like I'm showing you just highlights. Following the same class of problems, we went back to something we had done much earlier. Now, remember, I just talked about the case where the bead medium is crystalline. At slightly lower packing fraction, the bead medium is a dense fluid. Okay. Again, it's a fluid on a substrate, so its hydrodynamics is that of a fluid with a sort of global damping of the momentum. So it's, for those of you who do slow flows, it's Brinkman hydrodynamics, not just Stokes hydrodynamics. Anyway, but we decided to go back to the case of the fluid bead medium. About 10 years back, we had studied flocking induced by interactions mediated by the beads. But we sort of ignored the role of the density. So we decided to go back and look at that problem again. Sort of staying in regimes, in settings where flow is not important, but the interaction of motile particles with the density field of the medium is important. We discovered a very interesting new kind of condensation phenomenon. Okay, what we found basically, this is sort of the centerpiece of Roshan's PhD work. So this is as a function of, at low rod fraction, as a function of bead fraction. Here, nothing much is happening. Here, they're starting to move kind of coherently. Here, the rods are kind of precipitating, falling out from the bead mixture. They're demixing from the beads. But what's most interesting is here, it's already happened, unfortunately. The rods condense, but they condense into a little one-dimensional, just a strip, like a little monolayer membrane in 2 dimensions, right? And so this was intriguing. It's a kind of weird self-assembly which is somehow happening. It's the same thing. It's like it's an interface, this thing. And the density here and the density here are different. This is fairly packed, this is very packed. It's a small difference. I'll show you more dramatic examples of it. This is what? Yeah, so the way it happens, if you do a simulation, which means you don't have walls now, you have periodic boundary conditions, these guys assemble, they find each other and assemble into just one row. And that's really all they want to do. Unless you put in a lot more rods, they don't form anything more ramified or higher dimensional. You can do this in a quasi 1D geometry. Here, I don't know how far I'm going to get, let's see. So this is isotropic and kind of velocity aligned flock, and then here you get something really cool. So you see what happens here. You can play it again. So watch this space. The contrast is not brilliant, but if you look closely, you'll see that you get a low density region and a high density region. And the high density region is mobilized by basically a tiny number of these guys, right? This is sort of order 1 number of motile particles, not an order system size number. Okay, so these guys are able to, sort of what military people call a pincer movement, capture this blob of particles. And you can see the same thing and a little bit more fun. These again are experiments. You can get a single interface there, which moves along and pushes all this stuff, or you can get 2 like this that trap. And it depends, here it depends really on the concentration of the motile particles. So you got the beads, and here you keep the bead fraction fixed at 71%, and you sort of titrate in a few rods, a few more rods, a few more rods. And what you can get is this many motile particles pushing that many. Which, I mean, should surprise you, because what it means is, remember, if you didn't have this tiny, like, homeopathic concentration of rods, the beads will do nothing. They'll just sort of jitter around and do nothing. They will not condense. They won't start moving in some direction. They won't capture nothing. They're just hard beads. This tiny concentration of rods is able to condense a bulk quantity of beads. So it should give you pause, because condensation is a bulk phenomenon, and the physics of a sub-bulk amount, an order 1 number of particles, is somehow affecting order n number of particles. So it's a little weird, at least. And we played around, as I said, because we have this simulation which has everything in it. It's, you can actually ask, can you change the, okay, really. Let me show you a little. Let me just show you at least that you can double the system size in the simulation and still get the same phenomenon. So somehow what's happening, and we kind of, and by the way, you also notice that you had a huge density contrast or a small, but you can actually play around in the simulation of the propulsive force and get things that have a much more modest density contrast instead. So you can go from having a shock to just having dense, low density phase separation. So this is condensation of a bunch of particles whose only interaction with each other is repulsion, engineered by just one little strip of motile particles, sort of a self-assembled active strand. Okay. This movie's over. Okay. This brings up the question that Shana asked, which is this business about, this is a shock. A shock means you're exceeding some critical velocity in the system. But this whole system is really sitting on a substrate. So I don't know what the velocity scale is. Maybe it's the single step velocity, because these particles walk by bounding one step at a time. So even though there are no sound waves as such in these systems, maybe that's the speed involved. I'm not sure. Okay. The simple theory, for which I'll basically not even show you, I think I won't show you the equations, is just this. Motile rods, you take one motile rod, it pushes the beads, so it sort of bulldozes the beads. What it means is that if you start with the region where the bead density is uniform, and you have a few motile rods, they'll push, thereby creating a higher bead density in front of them than behind them. So part one of the story is, the mere movement of the rods creates a density gradient pointing in the direction in which the rods are moving. The second part is that rods, in fact, just for steric reasons, it's at least plausible to think that because the rods are tapered, statistically it's more likely that they'll sit with their pointy end in high densities and their fat round end in low densities. If you buy those two, then this gives you a positive feedback mechanism for the rods to create an interface between low density and high density, and then to situate themselves at the interface, thereby kind of stapling the interface. Okay. And it's also naturally, non-reciprocal physics is hidden here in the most trivial manner. The rods point towards low density for steric reasons, and because they are motile, they move. That means the rods are moving towards the beads. But the rods are pushing the beads, so the beads are moving away from the rods. So again, for absolutely elementary reasons, this interaction is non-reciprocal, and is only possible because the rods are motile. Motile means autonomously self-propelled. By the way, this system, I call it self-propelled, but it's actually converting the shaking energy into motion in the plane. But that's okay. I mean, all movement is energy conversion. Right? So this vibration is like the nutrient bath for these creatures. All right. I will skip the maths. I'll just show you that you can do, you can find a diffusive instability provided the tendency of the rods to push the beads and the tendency of the rods to point towards the beads, that combination is large enough and positive. Okay? You get a diffusive instability. That's all I will say about this. You can also do a little bit more maths to calculate how many beads a given rod can push. It turns out you can I will skip it. What you'll end up getting is that the bead profile ahead of a single layer of row of rods has an exponential decay length which gets bigger and bigger as the compression modulus of that bead bed gets larger and larger. So the more packed it is, the more slowly it decays. So really you can transmit your movement faithfully to almost any distance, because what you're doing is you're pushing something which, because it's effectively incompressible, sends whatever you're doing to the other end directly. Okay. It's important to note in all of this that all of this makes sense because there's no inertia. So it doesn't, how heavy a bead bed it is, none of that matters. It's pushing one step at a time, like that. Okay. I don't know. I think I'll skip the caustic, and I'll come to the last bit. Yeah. So I've given you one singular. I've given you non-mutual feelings. I've given you one singular structure. There are other singular structures in swimmers, in bulk fluid, in ambient flows, which I can't give you. Let me tell you a little bit about the mechanics of chiral active systems. That mechanics is very odd. But actually, that's not the only mechanics that's odd. You can have, okay, let me say what I mean by odd mechanics. Essentially, it means, for example, you squeeze something isotropically and it turns. Or you apply pure shear to something and pure shear stress and it responds with a simple shear strain. Those kinds of things. Okay. You've seen things like that in a different sense. When you have a child stop with one of those little helical things, you push down on it and it turns this way. So these sort of energy conversion with handedness is very, very common. It just depends on having the right structural element. So what I'm saying is that if you have a macroscopic system which has internal energy dissipating processes going on all the time, then if the system has chirality, its mechanics will be weird in these ways. Okay. So for example, here I don't even have chirality. I just have a collection of particles settling. If it's settling downwards, then if these guys are closer together, they settle faster. That gives you a tilt. That means that horizontal displacements are affecting the vertical motion. Now you have a tilt, and that means you've got a gradient of the vertical displacement, and that will affect the horizontal motion. So actually, even in externally driven systems like sedimentation, this kind of odd or non-reciprocal mechanics is very, very common. This is stuff we worked on recently and a long time ago, and it's got lots of cool physics which I would commend to your attention, but I won't talk about it today. So odd mechanics, very quick introduction, is supposing you have a system, again, let's forget inertia, let's write our equations of motion just as force balance. So let's say I have drag balanced by some kind of restoring force and maybe noise. Yeah? Question? So then the kinetic coefficient matrix is symmetric for reasons that Rangarajan taught us if the system is at thermal equilibrium. The restoring force matrix, if it comes from an energy function, is automatically symmetric. If you imagine a system now that's not at thermal equilibrium, but in a driven state, then generically you can imagine writing down these as the simplest types of equations of motion for that system, but in which these rules are broken. Actually, you know this, okay? For example, an odd drag is something you all know. Everybody who knows Wasim Akram knows this. Okay, so the ball should have been spherical. My apologies. Please transform it mentally so the ball is spherical. You know that the mere fact that the seam is inclined with respect to the direction of motion means that the force and the velocity are not parallel. So if this whole thing sounds oddly familiar, it is. There's lots of papers on this, but this seems to be relatively recent. In these systems, if you break either of these strongly enough, either of these symmetries strongly enough, then you'll find that even though the dynamical equations that you're writing down don't have mechanical inertia, they're just drag force balanced by quote-unquote elastic force, you'll get oscillatory response. Again, you kind of know that do you know that? Yeah, I mean, you know that in a very silly case. You know that in the case where you only have velocities and no positions. If you have a Lorentz force on a particle in a magnetic field, then the dynamics of the velocity is oscillatory in that sense. But here, breaking symmetry in the position dependent rather than velocity dependent part of the story requires being out of equilibrium. A Hall contribution to drag only requires a magnetic field. It can also be broken by particles being spinning or something like that, but you don't need it. So anyway, we studied, we found very interesting examples of this kind of oddness in systems which are somewhat complicated to describe. They're three-dimensional. In one direction, the molecule, you can shear them freely. In the remaining two directions, they're a crystal. So it's like, imagine you have a liquid column, another liquid column, another liquid column, and the cross-section is a two-dimensional crystal, the third direction is liquid. So in principle, the axon nerve cell, in other words, has an internal structure which is columnar packing. It has activity, and in addition, it has a polarity. That direction and that direction are not the same. So this is the case in which we found the most interesting effects. We wrote down a theory of systems of this sort using a dynamic density wave theory, taking into account the kinds of stresses that must arise in active systems. I will not show you equations for this, and viscous hydrodynamics. And what we predicted was that these systems generically, if they had these three features, would have elastic oscillations without inertia. And because you're operating in the regime of viscous hydrodynamics, the frequencies of these oscillations will go to a non-zero value in the zero wave number limit. Okay? And so we can predict these in great detail. Basically, any system which has a natural internal active scale of stress and a viscosity has a time scale. That time scale can be the time scale of instability, the relaxation time of a stable mode, or an oscillation. With chirality, polarity, and activity, it turns out it gives you oscillations. And this is the kind of odd mechanics that we predicted. So we predicted these things in enough detail that the sufficiently interested or sufficiently jobless experimenter can try to go and look for them in an experimental system. And we predict things like frequency as a function of direction and so forth. Anyway, I'll stop. I've told you a bunch of weakly connected to each other stories on non-reciprocal pursuit and capture, a weird active kind of condensation, some quite odd mechanics. There's lots and lots of open directions. It's a great field also in which to do experiments, and I thank you for your attention.
Thank you very much, Professor Sriram, for the wonderful talk. We have some time for questions, please.
Hi.
Is there an example of active condensation in the colloids world?
So I'll tell you what there is. It turns out, when I gave a talk on this a few months ago at a conference, and was told that they see something like this in the following. It's not really the same. Imagine you've got microtubules and two species of motors which walk in opposite directions. Okay, KF blah 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 something and some other alphanumeric which walk in opposite directions on the microtubule. Then you can get a situation which you've got. And the difference between that problem and ours is, in ours, the long and polar objects are active, and the beads are passive. In their system, the motors are the active things, and the filaments aren't. The filaments are just guide rails. Okay, but it doesn't really matter. There, what they find is you get a segregation of these two species, and it's stabilized by this. So this just came out. This came out, I think, a little bit after our paper, but I think by the time they heard about it, it was already accepted, and they couldn't point out the connection to ours. So this is work, I forget who the experimenters are, but Jean-François Joanny is one of the people. So it's sort of like this. They don't get this really absurd thing of an order one number of elongated particles producing an order n effect. Maybe because things aren't dense enough, I don't know. The same question, the question comes up in our case also. Why do we never see a spinodal decomposition pattern? We are seeing condensation, dense and low density. So you should actually see, what we see is, I can't even describe it as nucleation. If you watch the movies, those little motile guys are sort of wandering around aimlessly, find each other, and then form a row. And that's it. So it's something like nucleation, but I don't know if it is card-carrying nucleation.
Sir Arundan. Yeah. Thanks, Sriram, for a beautiful talk. Your title is indeed a good marketing strategy. It brought me here.
That's why you came, right? Yeah.
my question is about this non-reciprocal interaction. In all the talk I give, I just point out that it's not possible for atoms and molecules. It is possible for humans.
Correct. The point
You
is
see-
what degree, I think the key ingredient is you need to have some kind of sustained energy dissipation taking place. That is, you need to have a one-way flux of energy, you need to break time reversal invariance in a dissipative way, and then all these things can happen. And I've shown you, you should be at least convinced that the example I showed you was
Yeah, I
so
mean,
childish, right? I mean, there was no chemistry, there was no biology, there was nothing, there was just...
My follow-up question is that
Yeah.
we keep discussing about how did life come?
Yeah.
When did these atoms and molecules get life? Is there any hope this approach would take?
So I mean,
us-
I think the better statement is I think folks like me who work on these very simple models should talk to origin of life people like this. Who is this guy at University College London? Fantastic book called Nick Lane, right? Yeah. So we should actually. It's more a question that we should start paying attention to those kinds of questions, and maybe we'll at least learn something, and maybe we can contribute something. So I don't know for sure, but the general question, I mean, even in that book by Nick Lane, where he argues that these sort of lukewarm vents are places where some of these things could happen, I couldn't quite get from his story how the separation of ions of one type and another is sustained by the flow. There's questions of detail for which maybe one could think up baby calculations. Yeah. So I think that's a very relevant question, actually. Just I don't have a good, I've not done a good calculation for that.
Yeah, please.
So in your discussion of these rods and beads, you discussed how the behavior of the system changes when the densities are changed. But certainly these rods have to be bigger in size than the beads, and they have to be ellipsoidal with some asymmetry. So have you done any studies of
I can give you two cases. I can give you two extreme cases. If the rods are head-tail symmetric, then none of this stuff happens.
Oh, so the asymmetry
The polarity is crucial, right? Because it's a vector. It has to align with a gradient of a scalar.
Okay.
So a tensor will align with something bilinear in the gradient of a scalar.
Okay.
So if I have a density gradient, then the rod can sit like this or like this, but it won't push anything anyway.
Okay.
So it's important. Very, very simple symmetry arguments are actually all you need to get this. So that vectoriality is important. But you could imagine doing other, if they're chiral, Roshan is now working on some of those things, other things happen. But yeah, that's the crucial thing.
Okay. So and how large this asymmetry has to be? Is there some sort
The trouble is, these are not,
which you can, I think, quantify?
Yeah, so what it will do is changing those parameters will move you around in the phase diagram. Because what you saw was the diffusive instability. There's, let's say you assume the beads have some diffusion coefficient, and this active process in effect gives you phase separation by pushing the diffusion constant closer and closer to zero by a competing process. The strength of that competing process depends on two things: how hard the rods push the beads, and how asymmetrical the rods are, so that they like very strongly to sit with their rear ends in low density and their pointy front ends in high density. So those will move you around in the phase diagram. I think that's essentially what it is.
Hello, sir. Thank you for the wonderful talk. I have two questions. One, naively, you already Hi.
No, I just walked into the light, sorry.
Okay.
Yeah.
So you already explained the dynamics, but what I still don't understand is in this chasing motion, what prevents collision? Because
The thing is that nobody is moving far. All these things, they're actually walking. They're sort of shuffling along.
Okay.
So they're not flying. So what happens to be a given move, it's every 5 milliseconds or whatever it is, it executes one little forward shuffle. It also sometimes goes back. It on average goes in the direction which it's pointing. That direction turns. So when these guys come towards each other, there's also some beads in the way. So then they're not like projectiles. They're really like they're practically crawling.
follow.
So they will come up against each other. They collide in the sense they exclude each other. And in fact, as a result, if you have many rods, they'll start to line up and form the kinds of things you saw. You saw those rows and things. So that happens.
So the follow-up question is, from what I understand, the inter-rod space is controlled by the vibration energy that we provide.
The inter-rod space meaning?
How close two rods can get to each other.
I mean, if you strew them on a surface, they will tend, if you vibrate, they'll sort of distribute more or less evenly. And the inter-rod spacing is dictated just by how many you put on there, divided by the area, right? I mean, there is the meaning, the vibration doesn't change the spacing between them. It's not like thermal expansion. It's not like that.
Okay,
Yeah.
thank you.
It's more, there is, unless they start to condense, they kind of, in a time average sense, have some uniform density, which is number of particles divided by total area. They tend to go everywhere.
So just to reiterate, the condensation phenomena is dominantly controlled by the density of...
Yeah, so it looks like, I mean, there are two things. One is that we see the condensation when the bead density gets big enough. And if we increase the number of rods, if there are too few, for example, in that channel geometry, if there are so few rods, they can't even fill one width, then nothing happens. But that's a very bad answer for a theoretician, because theoreticians like to talk in terms of number per unit area, number per unit volume. I'm saying just number per width, which is, it bothers me. I haven't come to terms with it.
Sorry, lastly.
Yeah, sure.
Does increasing density change the structures of the condensate form? Like I saw one of it was...
Yeah, I'll tell you, actually, it's a very good question. Even though I kept calling it condensation, actually, when you condense these guys, it's not just condensed, it's crystalline. We haven't been able to make a liquid. I don't know the reason for that, but a similar effect takes place in another class of problems which some people in this room have worked on, Probal, for example, which is supposing you, for some reason, you decide to study a collection of particles in which there are two types, each of which is coupled to its own personal heat bath at a different temperature. So let's say there's temperature A and temperature B. Don't ask why. It turns out it's an approximate model of something that goes on inside chromatin, inside the nucleus, okay? But in those two temperature models also, in simple two temperature models, when a hot low density thing condenses a cold high density bit, that thing tends to condense into a crystal rather than just a liquid, and you have to work rather harder to make a liquid. So we don't really know. In fact, the referee scolded us for calling it condensation, because he said, look, it's just a crystal, it's just a jam. So anyway, I don't know about other structures. For spherical particles, most likely the only two possibilities are a high density fluid and a crystal. But for other shapes of particles, you could imagine other things.
Thank you, sir.
Yeah, thanks for the questions.
We can take up one more question.
What extent are the dynamics of the rods governed by the shape symmetry of the particles, or even the sizes?
So, I mean, the point is, of the particles, meaning of the beads.
Of the beads, yes.
So, I mean, we haven't looked actually at what the rods do when confronted with, tapered rods and pneumatic, sort of head-tail symmetric rods might also interact in an interesting way. We haven't looked much at that.
The beads are elliptical.
Yeah, so things will change. Yeah. Roshan, you want to do another PhD?
Okay, one more question. So, theories that you have are hydrodynamic theories.
Yeah.
But if you look at the kinetic theory, is there something new that you would expect to see?
Yeah, I mean, I think the thing is that, how to put it? People, for systems like this, I mean, not details of, okay, first of all, when you say kinetic theory, you want something that's mechanically faithful to everything in here, inelasticity, static friction, all that stuff, or you just want to have particles, active Brownian particles or something like that. Yeah, so the people have built the continuum theories from those kinetic theories. One of the things that nobody has done very well is to worry about the nature of the noise. Now, of course, the noise has some minimal constraint. It has to conserve the number of particles, and it's up against no other serious issue in these vibrated monolayer systems. In the bulk hydrodynamic systems, it's different. But even there, the strength of the noise in a given region. So, the strength of noise, supposing you ask, if you coarse grain your microscopic, stochastic equations and build PDEs, those PDEs will be stochastic PDEs in which the noise strength for the densities of intensive quantities the noise, RMS noise will be proportional to the square root of the local density. And the noise in equations for fields corresponding to intensive quantities will be proportional to something like 1 upon the square root of the density. These density dependencies of the noises are things that everybody pays lip service to and almost nobody actually does calculations with. So I don't know.
Okay, if there are no further questions, please join me.
There's one here.
Yeah, one last question. Yeah, please go ahead.
So for the bulk condensation due to active interface, I see dimension and the periodic boundary condition plays a crucial role.
No, I don't think periodic boundary condition. No, I think you can make the same thing happen in some less pretty way if you just have a box with walls.
Okay.
Yeah.
So there are the other ways other than.
Yeah, I mean the periodic boundary conditions is, okay, the channel geometry is convenient because if you want a moving state, you need some place for it to move, and this is one way of doing it. Although I say that with confidence, it's just because, it's a bad habit. Because actually, the effect of boundaries on bulk in active systems is much worse and much more poorly understood than in ordinary equilibrium systems. So there are puzzles lurking there which we haven't dealt with. So that's a very valid thing to ask.
Thank you. Please join me thanking Professor.
Thanks a lot.
Wonderful talk, and please wait for a minute.
Do I have to keep the mic on?
It's fine.
Okay.
Thank you very much.
Thank you. Thanks a lot. Thank you very much. Thank you. Thank you very much. Thanks a lot.
I invite you, all of you, to join for high tea outside.
Thanks. Okay. Hey, thanks. Thanks a lot. Thanks for coming. Despite the weather, it was a reasonable turnout.
Good, yeah.
And not all physics. Not only physics.
No, there are,
Yeah, enough other people. Yeah. Yes, sir. We are somehow, it's not just condensation. Because it's just phase separation condensation. I like to use phase separation when there are two compounds. The contrast is between high bead density and low bead density. So I'm saying it's only the rods are just a little agent. The thing that's condensing is the bead density. When you have one component